First, thank you so much to everybody here for coming out to hear my talk today. I really appreciate it. Hopefully it's good for you, entertaining for you. And thanks so much to the organizing team for putting together this awesome conference and giving us a chance to come together and learn some cool stuff. So hello, I'm Eli. I make some weird stuff on the internet. Sometimes this weird stuff happens at a company called Social Tables, a startup in my hometown of Washington, D.C., where I do kind of an even split, I guess, between front-end and Node.js and like WebGL graphics programming type stuff. I also organize the DC CodePen meetup and make some funky, weird animations, 3D art, and games and stuff on the side. So today, I'll be shrieking about why focusing on perceived performance above and beyond objective speed-based performance is a smart thing to do. A little bit to that end, how humans perceive time, and opening up a box of tricks to make sites and apps feel faster than they actually are, focusing in on techniques that recognize the best impact for a minimum developer effort. And I'll close up by talking about a technique called predictive preloading, which, when correctly applied, can completely eliminate perceived loading time. So why perceived performance matters? It matters because web performance, as a field, is fundamentally all about time. And time is a really funny thing. It can appear to speed up or slow down. It can expand and contract. Sometimes it can even grind to a halt or even run backwards. For some people, time may not even really exist at all. But for those of us for whom time does exist, this difference is down to the dichotomy between objective clock-based time and subjective time, which is time that we perceive without any sort of artificial aids. And it's awesome that in the last couple of years especially, we've seen amazing, huge strides in objective performance between H2 and service workers, image optimization techniques, critical rendering path, all these automated build processes to help us make our sites physically faster. And we tend to do this, we optimize for objective time, we optimize for speed, because it's fundamentally easy to measure. We can make our site load by 300 milliseconds faster, and we have a number to point to show that we did such a great job. And we do this even with perceived performance. When you think about techniques like optimizing for the critical rendering path, time to first interactivity, font loading techniques, they're all fundamentally focused on objective time. They're focused on the clock. They're not necessarily focused on the subjective. And the million-dollar question that we don't often enough ask when we're celebrating over cutting our loading time by 500 milliseconds or whatever, is what if users don't notice? What if they can't notice? And the sad fact is, oftentimes they don't. The reason that they don't is this psychological principle called just noticeable difference, which defines that between sort of human observable phenomena, between stimuli, they have to be significantly different enough from each other in order for somebody to distinguish between the two. So if you show someone like a bright light bulb and a dim light bulb, and you ask them to identify what's the bright one will have to be some amount brighter than the dim one in order for that person to pick it out of a lineup. And the same thing is true of time. That in the type of time horizons that we care about in web performance, time differences of 20% or less are completely imperceptible, which means that if you improve the loading speed of your app or the response time for an API call by 20%, there is a very good chance that a large amount of your users will not notice, and it will make no difference. And because we're not focused on just getting back to zero or making improvements that users just barely notice, we're focused on trying to make an actual tangible impact and make our things better. We don't want to focus on objective speedups of 20%. We want to shoot for something more like 30%. And in a large, mature application where a lot of our sort of objective speed, low-hanging fruit's already taken care of, 30% can be a really big number. And the sad fact is, we don't live inside of a web performance blog post. In fact, the world that we live in oftentimes looks a little bit more like this. We don't hold all the cards all the time. Shipping this type of objective speed improvement might involve the efforts of many different teams working in many different repositories on different services and APIs, as well as a client-side application, maybe in different time zones or working in different languages. And it may not be an efficient use of the front-end team's time to ship these types of improvements, even if they are able to. It just might not be the most efficient thing. So my pitch for why focusing on perceived performance is smart and it's good is it represents better bang for developer buck, that we can make better, more observable, subjective improvements by focusing directly on the subjective than focusing on objective speed and hoping that the subjective follows suit. So in order to do that, we'll have to understand a little bit about the psychology of how people perceive time and how that works. So humans tend to break down activities between active and passive phases. Active phases are characterized by higher levels of mental activity. Passive phases are characterized by lower levels of mental activity. So everybody's heard the phrase, a watched pot never boils, right? This is an American idiom. It means that when you're bored and you're staring at a pot just waiting for it to boil, it can seem like time stretches on into eternity. And the data backs this up. This is true. Humans tend to overestimate time spent in passive phases by 36%. They feel 36% slower. And the reason for that is that the primary neurotransmitter associated with the perception of time is dopamine. So in states where you're not mentally engaged, you're not producing as much dopamine, time seems to stretch out. In times where you are mentally engaged or you are producing more dopamine, time seems to compress. So we do this every day. We divide our activities. Consider the idea of commuting to work. Sometimes or if you're driving to work. For those of us who live in the sticks, sometimes we have to do that. Consider sometimes you're on a side street, scooting along, actively, mentally engaged in the act of driving, and sometimes you're on a main arterial road, stuck in traffic and not mentally engaged, twiddling your thumbs, waiting for traffic in front of you to clear. And I know for me that this sort of passive phase of this activity, waiting in traffic, always seems to take longer. And this is the same on the web, too. So here's a little demo of me browsing Amazon for my next outfit. And you can see as I browse, I switch between active and passive phases. Active phases when I'm consuming content, when I'm interacting with the page, when I'm reading something, and passive when essentially I'm waiting for the next page to load. This transition does not happen immediately. It takes about 1 second for a user to make that transition from an active state to a passive state. So, psychology out of the way, what does this mean for us? We can really sort of do two genres of ways to do this. We can either keep users in an active state and do everything that we can to keep them from entering a passive mental state, or in times where end user entering a passive mental state is unavoidable, we can play some tricks and make some illusions that can make that time seem to pass more quickly. So, keeping users active. This is super important for short durations because as it takes 1 second for users to make a transition between an active to a passive phase, if we can get all of our loading done in that 1 second, we can keep them active and they never have any disruptions. They stay in flow. So we can do sort of 3 main easy things to help with this. 1, we can make sure that we don't tip our hand and go out of our way to tell users that they're waiting for something. We can make sure that we respond to users immediately, even if nothing is actually happening in the app. And we can change the event listeners that we use to be a little bit less conventional, but a little bit more responsive in order to get a head start on loading what we need to load. So first, let's talk about resisting the temptation to use loading indicators. And I know what you're thinking, right? Whoa, whoa, whoa. Slow down. Don't use loaders? No spinners? No progress bars? Isn't that what perceived performance is all about? And you're right, but before we learn how to use loaders, we need to learn how to not abuse loaders. So showing someone a spinner or a progress bar or some other loading indicator is a cue to users that they've entered a time where they have to wait for something. So what they're doing, if they're already in an active mental state and you're prematurely showing them a loader before they've naturally made that transition into a waiting state or a passive state, you're picking them up out of an active mental state and putting them in a passive mental state, which is having the opposite effect of what we want. It's making our app feel slower. So a good rule of thumb that you should carry with you always is only add loaders as your anticipated waiting time approaches 1 second. OK, so now that's out of the way, we can talk about how to actually keep users engaged. Having an app that feels immediate and present and tactile is super important because users like to have the idea that they can maintain this two-way dialogue with the user, with the app. So it's like it's right there with them, and having an app that responds immediately to every user interaction makes it feel like that app is holding up its end of that conversation. The quickest and easiest way to do this is to make sure that you apply active states to all of your elements. Active states work just like hover states, except that instead of firing when you mouse over, they fire when you click or touch on them. They're implemented in exactly the same way. They work in exactly the same way. They're super quick and easy to implement, which is why it's so unfortunate that there are so many sites and apps that don't implement active states at all, because they're such a quick win. Once you've done that, you can hone in on optimism, and not this kind of optimism, although this kind of optimism is still very, very important indeed. But what we're talking about here is an optimistically updating UI. So in a traditional UI or a pessimistic UI, we only update the user interface when we retrieve a response from a server. So the interface just exists to mirror what's out there in serverland. So that means when we click our like on our handsome goat photo, we make a request, and then we update the user interface, which is a little slow, although admittedly it's quite honest. We can take an alternate tack and immediately update the UI by optimistically assuming that that request will be successful. So the 99% of users that that request is successful for get a positive experience, and then for the 1% of users where that request isn't successful, then we can worry about a failure state when that happens. The last thing we can do to keep users active is to change the event listeners that we use to try and get a head start. So remember that it takes about 1 second to enter a passive state, which means that we can keep users active if we get all of our loading done. And that means that in order to do that, we have to react as soon as the user signals intent. And so when you think about the most sort of common event listener that we all use, which is the click handler, a user signals their intent to click on something by pushing their mouse button down. But a click event doesn't fire until the mouse button comes back up again. It's the mouse down event listener that fires when the mouse button goes down. And that means that there's this sort of amount of time where a user signaled their intent by pushing their mouse button down, and we haven't done anything, because we're still waiting for the mouse button to come back up again. So I made a quick little demo and submitted it to participants on Mechanical Turk to get an understanding of what sort of time duration we were dealing with, and we can do the same demo here now. So here I click on this button, and I held my mouse button down for 81 milliseconds. Do it again, 148, here 147, 124, and this pretty much squares with what I found, which is users tend to hold their mouse button down when they click on stuff for 100 to 150 milliseconds. To put it another way, that means that by switching to a mouse down event listener from a click event listener, it means we get a 100 to 150 millisecond head start in loading whatever we need to do right off the top, basically totally for free. And sort of by accident, in the same experiment, I found that users tended to hold their mouse button down a little bit longer on buttons and elements that had an active state applied to them. My theory is that subconsciously reacting to the page, responding to their input, they hold their mouse button down for a few extra frames as they sort of like observe the things that are happening on the page. And sort of by playing around with durations and things, I arrived at a sweet spot of 200 milliseconds for an active animation duration, giving you a plus 50 millisecond bonus for how long the user holds their mouse button down for, sort of totaling out like 150 to 200 millisecond head start, which isn't bad. We shouldn't scoff at that. This works on touch devices too. We just have to be a little bit more careful. We can begin our loading on touch start as long as we don't confirm and take action with whatever we've loaded until a touch end that hasn't been interrupted by some sort of threshold-bound touch move event. The reason for this is, of course, people on touch devices fire off touch move events when they're navigating around the page, when they're scrolling and doing all sorts of other gesture-based interactions. And we don't want to accidentally surprise them by opening up a new page or popping a modal or doing whatever we're doing because they're scrolling and their thumb happened to come down on a button. OK, so those are 3 quick and easy things to do that we can keep users active and help manage perceived loading in sort of the types of anticipated situations where loading is going to take less than 1 second. But what happens when loads take longer than that, 1 to 4 seconds or so? If you have a slower API or you're requesting large images, loading 3D models or any sort of large assets, this type of wait is common. And what happens is you really start to lose people as passive states last from 1 to 4 seconds. So it's really critical to get this right. We can do 3 sort of best bang for buck things here. One is choosing the type of animation that can create an optical illusion that time is moving more quickly than it actually is. The second thing that we can do is adapt our loading durations and indeed our entire loading scheme based on measuring each user's request and establishing a picture of what that user's connection speed is. And 3, if all else fails, we can distract them with shiny objects. So finally, we can talk about progress bars. A researcher named David Meister conducted research on queuing behavior, how people wait for things. And one of his key takeaways from this big study was that uncertain waits where people don't know how long they're going to be waiting for, feel longer than waits where they have an idea of how much time is left. And the reason for this is subconscious anxiety. Waiting for something is unpleasant. Not knowing when something is unpleasant will end, causes some anxiety. Anxiety suppresses dopamine production, which slows time down. Progress bars help us fix this because they give users a sense in relative terms of how long they have been waiting and how much longer they have left to go. But not all progress bars are created equal, and the right animation can make a tremendous, tremendous difference here. So a team of graduate students at Carnegie Mellon conducted a study where they found that progress bars that have bands in them or some sort of element within the bar that animate in the opposite direction of main progress bar flow feel like the progress bar is going faster. And furthermore, you can create the impression that the bar is moving faster still if those bars, bands, elements, or whatever accelerate as they go through their motion. This creates an optical illusion similar to the type that you experience when you're sitting on a train and you look out the window and you see another train passing you in the opposite direction, and it seems like your relative speeds have doubled. It's the same sort of illusion at play. And at the end of their study, what they concluded is that bars with accelerating bands make it seem like time is passing 12% faster than when they're given no loading indicator at all. And that 12% number may seem small, but if you recall that if you were taking an objective speed-based approach to solving this problem, you would have to improve the load time by 20% just to get people to notice any change at all. So by implementing the right sort of progress bar, you can achieve a 12% subjective speed up rather than having a 20% objective speed up just to get back to 0. So this represents real value for us as developers. All this great stuff about progress bars, and we've forgotten something. But what about spinners? I feel kind of meh about spinners, to be honest. And the reason that I feel meh about spinners is they're just not particularly versatile. If the loading time is going to take less than 1 second, we don't want to show users anything at all. And if it's any more than 2 seconds, we really, really need to show them some sort of loading animation that gives them a sense of how much longer they have to wait, which means that spinners are only really useful between 1 and 2 seconds, and during that time frame, a progress bar does a fine job too. The real reason that you seem to see spinners everywhere is that they're both A, honest, and they're easy to implement. In order to have a quote-unquote real progress bar, you need to set up some sort of polling endpoint or WebSocket connection so you can continuously update the progress bar with information about how the loading is going, which in a lot of small cases can represent complete overkill, which is why you see a lot of spinners and why most progress bars you see on the internet are completely fake. And by fake, I mean it's one static duration, like CSS animation, that just moves from left to right, and when the loading is done, you animate it to completion. And most progress bars are fake. Many are pretty bad. And the reason that they're really bad is because, like a clock that's only right twice a day, a broken clock, a fake progress bar with a fixed duration is only accurate if your connection speed is the same as the developer's. And if you're too fast, you get the problem where we're tipping our hand and we're showing them a loading indicator that they didn't need. And if it's too slow, it's even worse, because it animates to 95% and then just sits there mocking you and driving you crazy. And you'll leave this site unless it's Twitter and you're like me and you're addicted because it makes you feel bad. So if real progress bars are overkill and we need to use some sort of progress bar in order to give users certainty, what do? How do we make our fake progress bars better? And how we do this is with a technique called adaptive loading. So we can modulate the duration of our fake progress bars. We can make them more real by measuring our users' requests and adjusting the progress bar duration based on how long it takes users to complete requests as they move through an app, sort of get a sense of their connection speed. So here's some very simple, certified, non-scary code that we can go through to see how this works. I'm just zooming in a little bit so it's a little bit more readable. So here's like an init function that might run on app startup when you're hydrating state, but really you would want to do this anytime a user makes a request. Before you send it off, you take a high-resolution timestamp. Then when you get the response from very serious API URL, you take another timestamp and subtract out your first one to get how long that API round trip took to complete. You then pass that into some sort of function along with how long you expected that API call to take on sort of a representative connection that that you feel is representative of your users. And you divide them into each other, of the observed versus expected time, to get what I'm calling a performance scalar, which is one number that you can multiply to expected durations to make your progress bar durations more accurate. In order to make this more sense, we can talk about it in real terms. So if you expected this request to take 1 second, and a user has a slightly faster connection speed than your average user, and it only took them half a second, then your performance scalar would be 0.5. So for your next request where you want to show them a progress bar, and you expect that duration to take 2 seconds, you multiply in your performance scalar. 2 times 0.5 is 1. So you've cut the duration of the progress bar in half to reflect the user's connection speed being twice as quick. This is like the world's simplest example of how you could implement this. So before you go and do this in production, I want to talk about a couple things that I left out of the code example in the interest of both simplicity and universality. One, you want to make sure that you definitely normalize for either the resource size that you're requesting or the complexity of the API call that you're making, the type of payload they're sending, or what you would expect back. Because as everybody knows, or maybe not all API calls to the same endpoint are created equal. You can make a call to go request an image, and it can resolve way faster if it's a small image than a big image. So you don't want to throw off your performance scalar just because a user requested a small image than a big image. So you need to save like your resource size and metadata and factor that into your performance scalar before you start adjusting progress bars. The second thing you want to do, once you're comfortable using this to just adjust progress bar duration, which is the simplest thing you can do, is to start using performance scalar to adapt your entire loading scheme. So rather than just take this in and make a progress bar shorter or longer to reflect the user's conditions, you could, if the user's going really fast, decide to show them a spinner instead of a progress bar. Or you could show them no loading indicator at all. And if they have a really much slower connection, you could show them a progress bar with some explanation to give them context about why their wait is so long, or you could show them an animated splash screen or any number of other things. The third thing you want to do is to have some sort of automated way to set your baseline expected times. This technique is completely meaningless without accurate data about how long you would expect this to take with some sort of normalized connection that's reflective of your users. And so you can set this in some sort of integration test runner that makes real requests against real APIs if you are employing one. So that way, if like an API team ships a fix and suddenly an endpoint responds twice as fast, you won't have to alter any client-side code to reflect that new reality. Your integration test runner, as it's making these requests, will pick up that it's faster and write out to a file somewhere that you can use in your client-side app that, hey, the expected duration for this is now less. Now, as durations start to creep longer than 4 seconds, we have to resort to extreme means. Like Dr. Zoidberg, we've got to climb up on our rubber ball and juggle some torches in order to keep them involved and to pull them back into an active state. This isn't as degrading as you might think. Slack, which is a very respectful company, I've been told, conducts a masterclass in this. They take you from this initial animated, branded, fancy spinner into a splash screen with a motivational quote for you to read and consume and another loading indicator into your last observed content while they have an animated skeleton screen that populates in your channels and mixed messages. So they take you from loading screen to loading screen to loading screen to loading screen, constantly forcing you to adjust. They show you a motivational quote or something to read in order to make your mind active. So that what they're doing is, rather than just letting you chill in this passive state while it takes 12 seconds for this app to boot up, they're pulling you back into an active state continuously, over and over and over again, trying to keep you active and trying to make the time feel like it takes less. So, and game devs do this all the time. Games take forever to load. They often load off of spinning disk hard drives rather than straight up from memory. So they frequently have to deal with challenges that we don't as web developers in managing perceived loading, so we can learn from some of the things that they do. Here's a clip from FIFA, a soccer game, where I'm setting up a match between Argentina and Brazil, and I click A to play match. And instead of being taken into a loading screen or a progress bar, I'm taken into this interactive play space, where I can take some shots on goal, or dribble around, or play any number of mini games and little challenges, either alone or with a friend, rather than just staring at a loading screen. And then when I'm ready to be done, I can press start to start the actual game. And the reason that you don't see this as often as you do is that Namco held a patent on this for a long, long time. And that patent extended out both into mobile apps and the web, blocking you from ever using minigames or, quote, interactive loading experiences. So now that that patent has expired, I believe it expired late 2015, I would expect to start seeing these more and start feeling comfortable using interactive loading experiences in production when you expect loading to take a very significant amount of time, like 10 seconds or more. If this feels like cheating, that's basically because it is. But showing someone content that's completely extraneous, if it helps make the loading experience seem like it's going faster than it actually is, isn't so bad, and we're not really doing them a disservice. So finally, I want to talk about predictive preloading, which has the potential, if correctly applied, to completely eliminate all perceived loading. So if you remember, way back when, we were talking about that we wanted to react as soon as users signal intent. We were going to change our event listeners to make that happen. Well, what if we could predict their intent before they definitively signal it? Then we could get an even bigger head start if we could extrapolate this out. Game devs have to do this all the time. It's one of the techniques that they rely on, the tricks to manage loading time and keep it hidden from a player. So here's a clip that I'm going to play shortly from a game called Metroid Prime that came out years and years ago. And developers ran into some really stern hardware restrictions in making this game. They could only load a handful of rooms into memory at any one time. But on the other hand, they wanted to have this game that felt open and expansive, that didn't present loading screens to users and allowed players to pass through their experience seamlessly. So they created a mechanic that distant players could unlock doors by shooting them, which I thought was something that was only OK to do in Texas, but apparently works in space too. And that would unlock a door. And then, based on the user's current behavior of walking towards an unlocked door, they would load the room behind that door into memory as the player approached it. So they look at a current picture of the user's behavior, in this case moving towards an unlocked door, and they extrapolated that their intent was to move through the door and preloaded the room beyond it so there was no perceived load. The door just opens as you approach. We don't have to do this with crazy machine learning stuff, although you certainly could. In fact, I'd bet that there are plenty of people in this room who have already done this in production without necessarily realizing it. Show of hands, who's ever like lazy loaded content on scroll, lazy loaded images or whatever? See, plenty of people, lots of hands. That's predictive preloading at its essence. You're taking a picture of the user's current behavior, scrolling, and you are adjusting your idea of what their intent is by assuming that because they're scrolling, they want to access the next bit of content, which is an easy prediction to make. And you're preloading that content into the browser before they arrive at it so that for the user, it's completely seamless. That's what predictive preloading is. But more than just lazy loading content on scroll, we can take this idea and run way far with it. So take, for example, like the idea of a checkout form. So how this traditionally would work is we put in our name, and then your address, and then you go on to the next page. And we click checkout, and it's loading. In the next page, it's loading these icons for cards. It's loading specialized card validation JavaScript and order submission JavaScript that we've smartly split off. We've done some code splitting, and we've kept that bundle separate. And then we can load it when users click the button. That's what you normally would do. We can also make an assumption that because this form has many steps, and that because a user is engaged in filling out towards the end of the form, that they were likely to want to move on to the next step, which is exactly what we did. We preloaded the page while I was typing, and there's no perceived load. This is something that you can do in basically every form that you have that has more than one step right now. It's a very easy assumption to make that if a user is approaching the end of form step A, that they want to go to form step B. And you can preload form step B before they get there. In this case, we were able to predict that 2 seconds in advance, which was way more than enough time to load that next view. And depending on how early you feel comfortable preloading the next page based on data on your own users, you could push this even further and get an even bigger head start. While this technique is particularly well suited to things like forms and linear flows, it can also be done with more complex user interactions, like clicking a button. So our sort of baseline here is this isolated big call to action button, and we're going to click it, and we're going to load a 3D model to play with in this little viewport. Yay, we got a 3D model, fun. Now, remember that loading on mouse down is faster than loading on click. Well, what if we could take that a step further and load on hover, which is what I did for a long, long time before realizing that you could, more than just loading on hover, you could study the pattern of mouse deceleration and start loading things as the mouse cursor decelerates towards an object. And you can pair these two behavioral quirks that people like to watch hovers, and that people necessarily have to slow their mouse cursor as they approach something they're going to click on. You can pair these two together to help preload a button with a high level of accuracy and with like far out enough to make a real substantive difference. So we're going to exploit these two behavioral quirks together, that people tend to watch hovers and that people necessarily slow their cursor. So I submitted a little demo to people on Mechanical Turk, asking them to evaluate an app that I made. And really, all I was doing is studying how long they hovered on buttons before they clicked on them. And I showed them a variety of different things. And what I found is that people were more willing to watch fancy, elaborate hovers like this one with this fancy, gooey liquid fill than they were buttons that were a little bit more simple, like this one with its little slashy fill. And what I found after much study was that fancy hovers, and I'm defining fancy as a very scientific term, where what I basically mean by that is there's more than one element of motion in the animation, and users are unlikely to have seen something like it recently. And that they were willing to watch those animations for longer, up to a sweet spot of about 600 milliseconds. That factor does fall off as they encounter that hover animation more and more and more. But the fall off is less pronounced for animations that are fancy, because I think people enjoy watching them and experiencing them. So that'll buy us something like 600 milliseconds. The second thing that we can do is use a library developed by a developer called Callum McRae at a company called Sam Knows. And this was open source like 2 weeks ago, so it's still very new. But I wanted to make sure that I mentioned it today because I'm so excited about its potential. How FutureLink works is it tracks cursor position and speed. The red lines are deceleration, and the green dots are sort of where FutureLink is predicting the cursor is going to end up. So how it works is it takes not just deceleration, but the rate of deceleration to predict the cursor's landing spot should that rate of deceleration stay the same. And so it starts plotting where it thinks it's going to be. And once it gets enough sort of plots in an area around a link or a button or whatever element that you pass into the FutureLink constructor, you can trigger a function when it predicts a click. So we're going to combine those two things together, the tendency to watch hovers and FutureLink link prediction, to see how long of a performance gain we can get, to see how far out we can predict a click before the click occurs. I'm going to turn on a little debug information here so I can see my cursor speed. So blue is acceleration, red is deceleration, and here we go. And we've predicted a click, hovered, and my demo broke. Demo gods, god damn it. There we go. And so we were able to cut like 80% of our load right off the top just by combining these two behavioral quirks together. And that was able to give us like 1.5 seconds. And it really depends based on how big the element is and how isolated it is. So the more isolated the element is, the bigger sort of prediction radius you can have around it. And so the further out you can accurately predict a click, and the more head start you can get. But in this case, we were able to get about 1.5 seconds. And in places where I've implemented it on projects, that's pretty much what I've seen. So predictive preloading is a super powerful tool, right? We can completely hide our perceived loading in certain cases. But with great power comes great responsibility. We have to make sure that we use this wisely. Whenever we make predictions about user behavior, we will get it wrong some of the time. That means that some users will have resources loaded, JavaScript loaded, and they're never going to use them. So we need to make sure that we mitigate that risk with data. study user behavior flows, study heat maps to understand where predictive preloading will have the greatest impact with the greatest accuracy. And then the first thing you want to do is make sure you implement it dry. So if you're putting future link on a button, instead of that function firing some asset requests when it predicts a click, instead, just fire a little piece of analytics saying, hey, I've predicted a click on this button. And then you can wait to see if that prediction was successful or not and build a picture of your false positive rate. And if you're comfortable with your false positive rate out there in production with actual users, then you can decide for yourself whether predictive preloading is a good fit. For me, that's about a 10% false positive rate is something that I'm comfortable with. So TLDR. Perceived performance is important because right now, for many mature web apps, perceived performance represents low-hanging fruit. It allows you to directly address subjective perceptions rather than simply focusing on the objective, chipping away at both diminishing returns and the just noticeable difference threshold. We can do this by making sure that our apps are immediate and responsive to user input and offer them real live feedback. We can make sure that we tailor our solution to each individual user and indeed each individual session to make sure that it suits both them, the resource that they're requesting, and their connection speed. We need to react quickly to user input by changing the event listeners that we use and extrapolate user intent to get a bigger advantage wherever we can with predictive preloading. We can introduce predictive preloading bit by bit. It's not something that should be implemented all at once or indeed implemented all over an application. Pick your spots where you think it's going to have impact, study it first, and then implement it. At the end of the day, never forget that nobody browses the web with a stopwatch. Objective time doesn't matter. The only thing that really counts is the subjective. The only thing that really counts is how it feels. And if you're focusing on the subjective and you're focusing on the user's feeling, you're really focusing in on the user. And at the end of the day, that's really what we're all here to do. Thanks.